everybody. So, Uno Smith, I've worked in the computer industry for some years now. I'm an industrial designer originally, so I quite like tinkering with things. I quite like building and modeling and, doing all of those things. So I don't shy away from, from interesting DIY projects and that kind of stuff either. But my first passion really is in the software industry, and primarily in how people use software to do work. So obviously that entails quite a lot of data and processing. And I specialize in problem projects often, and I like to do work. I like to help solve those problems, usually by working with people and working with data mostly. Tonight we're going to cover quite a lot of topics. I want to try and blast through it fairly quickly. So obviously, I can't really go into depth in anything in 45 minutes. So this is a broad introduction to the world that I'm interested in. I will share as much as I can, and then we'll hopefully leave some time at the end for Q&A. And I will try not to waste too much time doing other things. Let's see if I can move that out the way as well. So, right, let's start with a definition, at least from my perspective. So what do I think fast data means? I think for me, fast data is practically real-time data, and I don't want to get into a debate about what real-time means. So the pedantic among us will say that real-time means, that it has to be absolutely real-time, and other people will then argue that doesn't really exist. So my definition is that it's practically real-time, and therefore, as far as we're concerned, the data is coming into us for processing, now, and needs to be dealt with. Often data at this speed is usually bigger than system memory, and that sort of forces a design paradigm that we've got to think through when it comes to building software systems to manage that. I will share a little bit of what I think some of the best ways are of doing so. It's also usually impractical to persist all of the data that we receive or generate, and that means that there's got to be a decision about what is kept. And when you start doing that, that means that you're effectively truncating the information in some way. Fast data is often prone to loss and noise, or interruption. If you think about something like satellite, the weather system data that comes off a satellite, there's only information available while the satellite's overhead. Same with GPS and various other bits. So you tend to get information that has gaps in it. And there are ways of dealing with that as well, and we'll try and cover a little bit of that kind of stuff as well. And then finally, when it comes to fast data, one of the key factors here is that it's relentless in its processing demand. So there isn't a gap to processing. You have to literally process the data as quickly as it comes through. You've got to deal with the fact that it often has gaps in it, and when you back up your system, or when things slow down, that presents you with lots of problems. There's usually not a way to queue the data or store it for later. There are some exceptions to doing that, so if you've ever read up on how CERN store data, that's a really interesting case study. They have their own website available. I'd recommend that for anybody that's interested in information, especially if you're new to the field. Then definitely go and look at how that's done, and then hopefully with my talk tonight, we'll cover some of the basics of how they think through those types of systems. So here's our reference model for the evening. This is the rover race, the first vehicle designed by Daniel Simon. He's an amazing product designer in his own right. He's quite famous for a number of designs. I think the one that most people know about is the podcopter in Oblivion with Tom Cruise. That was also a very interesting design. They're not necessarily practical all the time, and so he is a true designer in that sense, but in this case, this has become a real product. And if you look at the product, I've left the markup on it so that you can see just how much sensors are embedded in the system. It obviously carries an amount of compute on on board as well, which is traveling at speed and therefore subject to lots of G-force and all sorts of interesting things, that requires a special design in its own right. People who work in space often understand this problem as well. You have high G and potential high impact forces on a computer system that has all sorts of problems in it, to deal with that, and special chip construction and various other bits, and, systems for isolating the vibration. But fundamentally, a platform like this is really a sensor package, and that creates an enormous amount of information. So if you think that, if we just look at a few of these, there's cameras on here, LiDAR systems, radar systems, sensors. Internally, there's compute, battery storage, energy management. So there's a huge amount of information to deal with. And then primarily the big interesting part here, the reason why robo-races have been created, is to give people the experience of being in one of them without the danger of doing so. So there's a huge amount of telemetry that comes from the vehicle itself. And that is then passed to a system where, there's either processing done, broadcasting done, and obviously there's a two-way radio control system that controls the vehicle when it's being used. So it's effectively a drone. And what we're talking about here can be applied to regular drones as well. So if you're into drones and surveying and that kind of stuff, you can use the same kind of technology to enhance that package. And I know quite a few people in the industry that have built and have built drones, custom-made drones, quadcopter drones or hexacopters, and they have built systems around them to support that, to build further services off that. Right, so let's talk a little bit about some of the things that we need to start processing information. So let's assume, through the talk, we'll just sort of refer back to this when we need to. Primarily, I'm going to focus on the fact that data has been sent from this mobile system or autonomous system and into us. And I'm going to ignore the fact that there's, artificial intelligence running on the platform directly that's making decisions on the fly, because it's not that part that I think is important for me personally. But it's once you start getting this data off the platform in its operation, what do you do with it, right? So firstly, there are a couple of characteristics of a real-time system, especially to process data at that speed. And the first thing is that the system can't be blocking, it can't prevent data from coming through, because you all experience this on a daily basis. There's latency on your broadband, or when you try and download a film on Netflix, that is the same kind of activity. So you're waiting for something to happen, and it's usually a blocking process that prevents you from seeing something. And in most cases, for something like Netflix, that'll be caching. It'll just be storing the data so that it can be passed on to other people. When you process data at speed, obviously, it's happening so fast that you're not necessarily storing all of the information. And that means that when you do store state, and I would recommend that you read up on stateless processing as well, because storing state is quite hard in these systems. But when you do store state, it really is only eventually consistent. So you don't have the same concepts of a database of pushing data into a database and then being able to read that data straight away. So you tend to create a system that can write fast, and then eventually get to a position where you can read fast from it as well. But there's a gap in that processing time. Systems have to be fault tolerant, obviously, because if it expects data and you can't get data, or there's an interruption in the data, it kind of needs to just carry on from where it is, and understand that there's a gap. So usually there's some high resolution timers that I use to coordinate activity in these systems as well. The software that you use needs to be composable, because in most cases you want to assemble it in different ways. You may want to have a number of building blocks that you can reorder or assemble in different ways, or swap out if you need to. Obviously, the system has to be available, and it often has to be scalable. So depending on you know, on how much information you're going to retrieve and store and retain over the period. You know, your system will grow rapidly for a short while, and then you can, once you've done the processing, you can relax the you know, the processing demand on the system, and then, you know, end up in a lower state again with fewer resources. Typical problem like that scalability. If I always think about the National Lottery, which you know, which is where most of the tickets are bought in the 1 hour before the lottery actually closes. You know, that's where the bulk of the work happens. So clearly that system, you know, for the rest of the time isn't necessarily required. So they do scale it right back, you know, and make it available in short bursts. And that's usually through cloud scalability. So often, you know, the big cloud providers create that capability. Right, so we also need to understand events and streams, and this, I promise, this is the only code that I'll show tonight, so that we can talk a little bit about what they are and why they become important. You'll see that in the systems later. So the top block is an example of an event, and this is a bit of JavaScript code that creates an event, and it's not particularly complicated, but what it does is on line 8, it emits that event and with a payload. So the event has a name, and it's called event in this case, and then it has a payload attached to that, which is a number of arguments. So if I console log it there on line 5, if I push that onto the console, say if it's an event with parameters and the first and the second argument, it gives me what you can see right at the bottom on line 11. You know, it gives me that little string with the 2 parameters that comes out of the payload, and this concept of a name and a payload becomes quite useful in these types of systems, and we'll talk about that when we get there later. So events important. Understand that they are effectively just they're just a message with a payload that you can push through a system. Another thing to understand is how streams work, and here's that second block of code for the 8 lines in is a full working file server, which serves a single file. So, you know, it's not particularly complex. It's really simple stuff in terms of you know, the code aspect of it. But at the bottom there, you know, on line 5, that's where you create a read stream, and that read stream says it's connecting to a file called data.txt. And then on line 6, we take the stream and we pipe that to the response. So when you call the server on port 3000 at the bottom, it'll send you the content of what's in the data.txt file. And it'll do it in such a way that it immediately starts sending the data to you. It doesn't wait to read the file into memory, because often you can't read it into memory. It's usually too big. And I'm using a file here, but that can be anything. It can be another, you know, you can pipe to multiple things. You can pipe to another IP address. You can pipe to, you know, from a file to a file, or from a file to, in this case, it's an HTTP server, so a web server. So, and that concept of piping from one stream to another is also important. So you literally, you know, you create the stream and you pipe your functionality into it, so you can chain them along each other and create fairly complex systems that way. Right. Some of the patterns and protocols that we need to think about as well when we do this work is you know, there are a couple of things that people will recognize. So you've probably heard of pub/sub, and that's really publish and subscribe. It's a software pattern where you know, where you can have a part of the software publishes a series of events, and then other software components, or in fact other software systems, can subscribe to those events and act on them independently. And we'll have a little bit of a look at how that gets done to some extent. And what that gives you is, it gives you the possibility to create parallel processing type systems when you're starting to work with data. pub/sub relies on the observer pattern, and the observer really is just what it says. It's a piece of software that observes another piece of software or a data stream, and then acts on, you know, changes within that stream. The chain of responsibility we've talked a little bit about. and that is really a composing pattern to allow you to connect a number of systems or processes together in a specific order, so that you can pipe from one to the other. The chain of responsibility pattern then gives you a way of doing that and controlling the output. The command pattern, also quite an interesting software pattern to use, which is a little bit like the event that I showed you, in that a command is really a text instruction with a payload. And we use that quite a lot to store data, especially if you're telling a system what it's doing. We can use that to put messages on a message bus, and makes and have a big composed system that that can act on the commands and then take the payload and process that. If you have commands, you almost always have to have an interpreter, which is also a software pattern that allows you to read those commands and then do something based on the text that is being passed around. So it's not necessarily held in system memory all the time. You can read a command and understand what to do with it. And like I said before, systems are designed to write and read separately. So that's a concept called CQRS, or Command Query Responsibility Separation. And it's worth reading up on the pattern. It's quite an interesting concept. It's very different to monolithic software systems in the way that you build your system, because you really have a write side and then you have a separate read side. And that forces this disparity between consistency. So you only, you'll read your data later than when you've written it. It also goes hand in hand with event sourcing. So the command pattern and event sourcing and CQRS sort of make a very interesting combination. That is what most real-time systems, or for data processing at least, are based on. I'm not talking about hardware systems here. I'm talking about software processing or data processing systems. And then often to encode those commands, something that's becoming almost ubiquitous in the space is protocol buffers, which is a small schema and a mechanism for you to store data. It's a little bit like JSON data or a piece of text. It allows you to compile data into a small space, into a small message, and that helps. It's very fast to work with that. And it's becoming, it was originally done by Google or created by Google, but it's open source, so it's now being used in almost all of the software that I've seen in the last five or so years. And then the proper protocols, TCP, endpoint connectivity, if you have to have a connection that stays open, UDP and datagrams, if you have to have, for anything that can afford to be closed, or processed quickly and then be released. And then there's a number of streaming protocols as well. So RTP is real-time, I've forgotten the acronym, real-time something processing. And the RTSP is the stream version of that. So what you normally see if you see Netflix, you're probably looking at an RTSP stream. It's worth studying some of these things. So the responsibility patterns, or the chain of responsibility command, interpreter, observer, those are all called the Gang of Four patterns, and there's a number of places that talk about that. They're almost universally available in all languages. So it's worth, if there's a for the developers amongst the audience, have a look at them and try and understand what they are and how they work, and then how we can use them to build these systems. Right, so once we've got that, we can come up with a pseudo architecture. So we've done some research. We understand more or less how these systems will be composed. You can see my little car at the bottom there, up on the left-hand side underneath the mast, and then we receive all of that telemetry within the static system. And that's really, first thing is straight through a firewall, block out all of the noise, remove anything that's not from that system directly, from the car directly, and make sure that there's nothing, it's just a very easy way of removing all of the additional load on systems by putting a really fast firewall in place. And that usually then ends up in a set of processing servers. And then in the columns to the right, I'll just talk a little bit about what these patterns are and what they represent. So from the point that you are receiving data, that data is inbound into the system, and it comes through this as a stream. So at the top there, I'm representing a stream that moves from the server on the left to, just straight through to the right, and it has little packets of data in it. Depending on your architecture, they can already be in datagram format, or they can be just straight binary data from from the server. It could also already be composed into bits of information that you can use that has some sort of a lightweight schema attached to it. Underneath that, then you end up running an algorithm, and you can then make a decision about what you do with that algorithm. That's usually one of those stream little stream server that I showed you earlier in the second, in the code block. That little stream server will then read the data, but it will not consume the data. So it looks at the stream, reads the data, and in this case, that might pipe all of that information directly to disk, and we just store a copy of the stream as it comes through. When you start doing that, you very quickly run out of disk space and out of file space, and the limitations of Windows or Linux, depending on what you're doing. So you almost always have to start building in a sharding strategy. And for the data, if people understand this, we just split the stream into multiple outputs based on either time or on duration or on size, or we just pick a strategy to use to create multiple files and then store as much of that data as we want. But obviously there are decisions to make about how much of that data is kept in and what format that's done. You usually don't have time to compress the data at that point, because it's coming, as fast as your system can process. The nature of the stream then, because the stream is effectively flowing data through, you can have multiple subscribers. So this is also it follows the pub sub pattern. So in column 2, you have another subscriber that's looking at the stream, and it's doing something else. It's not doing the same as the first column. So in this case, we're running a processing engine that will apply a filter to the data, and it may pick specific bits of data out from the stream and then store that into a database. So the key thing here is that obviously in order to store it in the database, it needs to do so. The database needs to be able to accept the storage at the speed that you're processing it at. If you can't, then you have to queue the data, and there are systems that queue massive amounts of data, and then they slowly work their way through it. And that's usually the reason why you have column 1 is to keep a log of all the information that's coming through, so that you can at least process some of that information later. There's almost always a scaling problem when you start storing data into the database. So you can also apply a strategy like a sharding strategy there, or you can just use Elastic Cloud to scale out for the time that you need it. In which case that algorithm is usually a proxy of some sort that makes a decision where to put the data. So you might, if I take a simple example, if we took names out of the telephone book as fast as we can, then you would maybe sort that into 26 buckets of surname, so that you have all the S's and all the A's and all the C's and whatever's sorted into different elements. In the third column, it's roughly the same process, but your output doesn't necessarily have to be an endpoint like a file. It can still be binary data, or you can convert your data at that point, and then restream the data. So you can also push a secondary stream out, and you can go quite deep with this. You can do secondary and tertiary streams if you want. And then the same process applies. You can attach new processing to those streams as well. So you might want to simplify the data that's coming through, remove elements of, if it's not particularly interesting information, you might want to take out noise, so you cut the peaks and the troughs, and look at a simpler set of data, and then restream that to another system, like an analytics system in column 4 as an example, or an instrumentation system, or something that gives you a secondary value from that stream. I'm going to show you a slight variation on the next slide. So I've just changed this ever so slightly. So in between column 2 and 3 now, you can see that Column 2 is a consumer of the stream, so it then takes, and it ends, the stream ends in that component. So it's not passing the stream on for further processing. And what it does is it does its function, but it also pipes its functionality to, it pipes its own processing to another stream, to another processor to act on directly. And that stream happens to create a new stream for analytics, but it can also create a series of events here and call out to other systems that do similar tasks. So you can, if you think about what it does here, you can compose a very, very complicated architecture where you use these fairly simple patterns to do so. So you can call out to other systems, or you can just raise events, which is what that arrow represents to the right. And the events themselves can be, can either be logged or captured or retransmitted. You might want to send data back to your car, as an example, and that can be, come in for a pit stop, that kind of stuff. So those are the types of architectures that we need, right? So now we've got sort of all the concepts that we need to start building a system like this. So how do we then work with the data, right? How do we get data, and how do we start building a system like this? So for me, this is an interesting part, and this is where I have quite a lot of fun usually, because I quite like tinkering with stuff, like I said before. So you can hack existing data, and this, if you're just looking for binary data to play with, there's a huge amount of opportunity out there to get information. But I often take image data from a site like Unsplash, trim the header and the footer off, so that it's just binary data, and then process that data and see what I can do with it. That sort of leads to data bashing as well. So you can take a number of data sources and put them together and create your own data source, which is quite a useful exercise in its own right. You can also generate the data. So in the same way that I wrote that, or showed that little bit of code, it's not much more code. It's probably a page full of code to create a noisy system, that generates a noisy stream. And if you create two noisy systems, with different output lengths, then you can have you can combine the data, and therefore, if you're generating if you're generating like a waveform, for instance, you can have all sorts of interesting artifacts when, similar to when people do music processing and, combine different music streams together as well. So you can do that kind of work. It's not a lot of activity to learn. It's quite simple to actually get into doing that, and it's quite fun to play with data when you start generating data. My favorite is capturing data, and on the right-hand side there, I've got a number of things that I show that I play with, and that picture of the little RC car is one that I bought for one of my lads, and then he decided not to play with it anymore, so it became a little research platform for me. And it's very easy to attach a microcontroller to it, so something like an Arduino. The kit that you see on the top left there is an Arduino Uno from Elegoo, with a whole lot of sensors and all sorts of interesting bits to play with. And there's a picture there of 3 accelerometers as well. They're 3-axis accelerometers. Those 3 things together is less than £100. So, it's a really easy way to get into it. So, and you can have some fun driving around in the backyard and collecting vast amounts of data that resembles something at the larger scale. So this sort of led me into research, into model-based engineering, and sort of thinking about what that really meant, because a lot of the people that I work with take model-based engineering quite seriously. But for me, there's this sort of aspect of modeling, and and what that really means. There's a practical aspect to it as well, which I think often gets overlooked. We tend to spend a lot of time in our heads instead of in the garage. So I'd recommend that you try a bit of kit bashing with data bashing, and it's quite fun to do that kind of work as well. In the bottom right-hand corner, there's something called a HackRF. So if there are any amateur radio enthusiasts around, that's an incredible piece of kit. It's a software programmable radio, and you can, with a decent antenna setup, you can collect satellite data, you can collect radio station data, you can collect IoT data from, from machines running in the field, or if you drive past a power station, you'd be surprised at how much information is available for you to play with. Because it's broadcast, you can obviously, it's effectively open source at that point. So, there's surprising amounts of information that can be drawn from it. If you're interested in anything with space, then I would recommend you play with it with HackRF. It's a bit more expensive. It's in the region of about £300. But you can get one often secondhand. They are fun toys to play with, and it's quite easy to either get GPS data from it, or to get satellite, like weather satellite systems off one of the old Russian satellites, for instance. It doesn't take that much to do it, and I'd recommend you have a look for HackRF on YouTube, and you'll find loads of resources of interesting things that people do with that. I've got two other toys that I don't have pictures up here for, which is a GNSS receiver, which is a GNSS receiver, which is just a GPS receiver, but that can take data from any of the satellite systems. And I also have a personal firewall, which I've got a link to later, which I think is a really interesting piece of code. What I didn't realize is when I started doing this stuff is a lot of the chips that are manufactured in China call home. So when you start building something, they often send a little bit of data back to China. So I use a firewall to block that information, and also just to help protect from other influence. Especially if you start transmitting information, it's quite useful. Right. So now let's say that we've used one of these ideas to get to data. So we have data, and we usually, when you get your data, it looks a little bit like that, right? So, and you immediately faced with an interesting problem. So this is usually what raw data looks like when we get it into the system. It's fairly random. It's often gapped as it is there. It's very difficult to make sense of what the pattern is in there. And if you're a data scientist and somebody gives you this, then you sort of roll up your sleeves and you know that you're in for the long haul, because there's a lot of work to do. But there are, of course, ways of dealing with it. So before we do anything with the data, we've got to make a few decisions, and that is, do we keep all of the data, or can we discard some of the data? And that's not an obvious conversation to have in the beginning. It's not an obvious decision to make when you start out, because initially you keep everything, and then it's at some point, as you start to understand your systems and what the data means, you'll start throwing some of it away. It's just not practical to keep all of it. It's most of it's noise. And it really starts becoming practical to use when you start filtering the data and applying useful data transforms here. And depending on the types of data you work with, often things like the fast Fourier transform, or a number of filter sets give you the capability to analyze the data in a more simple way. That allows you to then look for patterns, and eventually to progressively enhance the information as well. So it's worth, once you start getting information, it's worth looking at how you can combine one or two data streams, that have already been filtered, because you may apply a filter to take out the noise in a data stream like this, but that has its own artifacts often. So you might want to have a filter that has a slightly different action to then give you slightly more noisy data, and then you can combine those two outputs into a new stream that you then feed into another system to act on. You obviously have to process the data once you've captured it, and then from there you can invoke multiple other streams for processing. So you can invoke secondary and tertiary processing streams from there. It's really, once you start composing a system like that, the system stays real time. The only thing that you're doing is you're introducing an element of latency. So when you filter, you're doing a bit of work, but once you stream out from that work, the next piece, the next processing function in the chain gets the data at the same speed that you're processing it. You know, so you sort of end up with introducing a bit of latency in your system, and that latency doesn't really matter how long it is, which is why I say that your system will only eventually be consistent. So when you stop receiving data, at some point, all of the data settles, and you've resolved your processing activity. Right. So I'll give you an example of a filter. So common filters are part of the Bayesian filter family, and the data are those little round dots. You know, that sort of represents the chaos that you see. And we instinctively know that there's a median in there somewhere. So if we could see what the median was, it would be that blue line, and then the purplish line is the Kalman filter output. So you can see that it settles fairly quickly on something that roughly approximates the clean mean data set that we expect. So it reduces the noise very quickly into an average data set. It's also very quick for processing. So there's some amazing Kalman filter algorithms, and it's definitely worth doing it. You can do it in any language. If you really, I do almost all of my work in JavaScript and on Node.js because it's easy to scale. But if you're a Python programmer, or if you work in C++, obviously, then there's some very fast implementations of this. One of the characteristics of a Kalman filter is that it settles quickly to the data set that you're looking at. So if you on the left-hand side, you can see there's a big swing, but it very quickly gets to that sort of mean. You can use it for prediction. So you can say that if you have a number of elements, you can sort of say, because it settles fairly quickly into the noise set, you can say that your next one will be this, within a certain variance. And if your weighting in the Kalman filter is correct, if you're looking at, say, temperature or something like that in a windstorm, then if it's increasing, then the Kalman filter will follow, and it'll tell you that it's increasing. And it tends to be quite accurate. So the problem with the Kalman filter itself is that that once it's settled into this, it really does averaging. So it really gives you a very close approximation of the average within the set that you're looking at. So that might not be of value if you're trying to understand the peaks and the troughs. So I sort of then, there's a lot of these, by the way. All the data scientists will know there's tons of ways of filtering, but usually this is the first level of work that you'll do, is to try and filter the data that you get in, and then maybe use this to feed your machine learning algorithms and various other bits. There's also, I tend to not look in the data science space for a lot of the stuff. So the next example I'm going to show you is out of the finance world. So these are, for the finance people, they'll recognize this instantly. These are Heikin-Ashi candles, and they have an interesting, bit of, store an interesting bit of information. So those 4 little candles that I've put on the right-hand side are the 4 different types that you get. I show you min, max, high, and low. And what makes Heikin-Ashi interesting is the fat bar. It will always start right in the middle of the previous, fat bar. So it is a sort of a self-averaging algorithm that looks at the latest data only. It's a lovely way of getting to of working through data. And obviously what this does is it reduces your data scope by timed blocks. So you'll measure data for, say, 5 seconds, for 10 seconds, and then draw a candle. So it'll give you min, max, high, low, and then you'll wait another 10 seconds, then draw the next candle. And then the moment you draw the next candle, you can start making decisions, you can start predicting. And there's an interesting pattern here. So candles that have like the green candle on the left of the 4, that have a flat bottom and a wick for the top. That candle indicates a potential upswing, so it indicates a potential increased growth, or upturn of your signal. The two in the middle are called indecision candles. So you don't act on the information, but then the one on the right-hand side shows you the inverse of the one on the left-hand side, and that's usually the first one of a prediction that says you're looking at a downturn. And it does the same thing when you look at data. And if you look at the main chart, you'll sort of recognize that pattern. And then usually a downturn for a while, a couple of indecision candles, then a strong signal in the opposite direction, and then an upturn for a while, and so on and so on. So what these do is they perturb very quickly. So you follow the chaos more closely. So you can then do things like they do in the finance industry, is moving averages, and over different periods. You can use all of that to enrich your data set, to start helping you, to start to make more sense of it and start to use it to make decisions. Often those decisions drive part of the architecture. So you may use the output of something like this to make a decision about where you should store data, or what you want to do with the system next, or what capacity it's reaching, those kind of things. So without filtering, I don't think you can do a huge amount of info. You can't possibly process all the information that you're looking at. But it is worth thinking about not just the industry that you're studying in, or your specialism, is to look outside of that as well, which is why I'm giving you a few different examples here. So a combination then of the first one and the second one gives you an interesting view, because you can say, there's an average that's following a trend, and then there's a perturbation on the average that you can also look at to see how that works by using a different measurement type or a different filter set. Right. We're virtually done with our talk. I just want to see where we are time-wise. We're absolutely on time. So I just want to show you a few resources. So I would recommend, if you're interested in this field, looking at Apache Kafka. It uses all of these principles: events, streaming, CQRS. It literally has all the principles we've talked about. Free and open source from the Apache Foundation. So you can download it tonight and actually play with it by the end of the night. Quite interesting to do stuff there. If you're looking for some resources to learn, I'd recommend you look at Confluent as a business. They've got quite a lot of free resource available on Apache. They seem to be betting a lot of their activity on this platform. So it is interesting. If your business doesn't allow open source software for whatever reason, this is not the only option. Most of the big cloud providers have similar capability, maybe not assembled in one place, but there's a number of commercial offerings as well. So when you start searching for Kafka, you'll find a whole lot of other things. Because I've worked mostly in JavaScript and not in Python, I use TensorFlow for processing, for a bit of machine learning, and for doing things like image recognition and or object recognition, that kind of stuff. And it's worth playing with that as well. Obviously, TensorFlow is also free and open source. I use IFTTT for creating events. Really handy if you want to turn your house lights on before you get there. So you can use your mobile phone location. If you've got the app on your phone, to trigger an event that tells your house to turn the lights on. So just before you get there. I do all my software development is in Svelte, as opposed to React, which is what a lot of people focus on nowadays for the front end. Most of my work is front end work and visualization. So I use that. It's a compiler instead of a framework. So I think it's going to be the next big thing. So I'm hedging all my bets on that as a tool. For any form of testing or for some lightweight codable transformation and data generation, I use Playwright. So it's both my testing system that I use for test rigs, and also to generate data with, and to part automate some of the work that I do. It's a lovely piece of kit. It's worth looking at that. If you're interested in data, or you're a statistician, you obviously know what R is. But if you're not in that space, then go have a look at the R project. It is a a set of tools and capability to do fairly interesting statistical analysis and querying. And if you're really serious about machine learning, you probably have to learn Python anyway, because that's what most of the algorithms are written in. And that seems to be where it is. I'm just not a particular fan of Python, so I tend to read the data and then go and try and do something, something in JavaScript rather. On the hardware side, talked about a few of these things. The firewall that I use is called Firewalla Gold. It's not a cheap piece of kit, but it is a wonderful piece of equipment. A friend of mine introduced me to it when he showed me what he built, and he won a competition for his layout. And it is just a phenomenal piece of kit, and everybody should have one. Not that I get anything for saying so, but you'd be surprised at just how much information you're not aware of that's being shared with other, with third parties that we just take for granted. So there's a number of places to go look. One of my favorite places, Amazon, and for things that are, if I'm desperate for something cheap, that I've usually sort of a hardware platform. If I need a new drone or something like that, I'll also go to Banggood. But like I said, the Chinese stuff tend to call home. So just be aware of that, depending on what work you're doing. So if you're working, especially if you're working in a secure space, probably not the best idea to drag one of those onto site. Right, I think that brings us to the end of the talk. I've